Okay, welcome everybody to Fernando Fachini's PhD defense. In the committee, we have Professor Krushik Khan, Professor Agun Julius, and both of the electrical computer and systems engineering department, and Professor Wanda Su, who is in Penn State. He's the external member. And please, Fernando, you can start. You have 50 minutes.
Have my time here. So thank you everybody for attending my thesis defense. I would like to share the research that I've done. The title of this presentation is Dynamic Modeling for Autonomous Microgrid Control and Resilient Operation. So the outline of my research and this presentation, I will begin with a brief introduction, the research scope, and the general overview. And then we'll go through a basic review of what Modelica and OpenMPSL are. I'll then discuss a little bit of the modeling of generic renewable sources that were utilized in the modeling of the microgrid systems. Then we'll go into depth in the resiliency and optimization of microgrids using model predictive control. Because of the time limitation, not all of the results and all of the things that I've done in the PhD are present in the thesis presentation, but they're highlighted and presented briefly on the other results section. And then we'll finish everything with conclusions. An introduction. So the research that I've developed is based on a project developed, sponsored by the Department of Energy, and it has a collaboration of universities and research groups, research labs. And the goal is to develop a holistic open source modeling platform for the optimal design of grid interactive efficient district energy systems. And these systems are a combination of thermal and electrical systems along with their integrated control. And the systems that we actually studied are university campus microgrids, and where we have a mix of traditional gas and steam power turbines and also renewable energy sources. And the overall goal of the project was to achieve a 25% total system energy efficiency, improved compared to the state of the art, and also to increase the number of continuous operations by at least 25%, which is related to the increase of resiliency. And the scope of my research is more focused on the resiliency aspect. Okay. The star component of all my research has to be the Modelica modeling language. For those that do not know, it's a modeling language that was created for solving complex multidisciplinary systems, modeling analysis problems. It's heavily used nowadays in the automotive, aerospace, and robotics field, but it's still in the early stages in power systems. And this is the opportunity that we have to develop the power system analysis library utilizing Modelica. Okay. Now I like to think about my research in terms of an analogy related to the Lego blocks. And I've developed components for OpenMPSL and other libraries. And these are the components that I've developed. So for the first Lego block that I've developed, I've made improvements to the OpenMPSL library with the creation of renewable energy models and models that were improved based on hardware in the loop experiments. The second Lego block that I've also implemented was my own library that is dedicated for simulating multi-domain motor models. And the third Lego block, which is the combination, which is the framework that uses MATLAB plus Dynmic and Modelica for model predictive control. And lastly, once you have these Lego blocks, you can combine these components that I've developed plus the components of other libraries to create system models with which I used to study and apply optimization. But for the time being, and because of the time limitations, the main topics that I'm going to address in this presentation are the first Lego block, which is related to renewables, the third Lego block, which is the MPC framework, and the utilization of the MPC framework into systems, and the proof of concept system microgrid, and the optimization of one of the university. Okay. So a little bit about basic review of what Modelica and OpenMPSL for those that do not know what it is. So Modelica is a modeling language, and it's run by the Modelica Association. And the objective of the Modelica Association is to coordinate the development of open access standards and open source software in the area of cyber-physical systems. It leads the development of the modeling language, the Modelica language, and it also develops the open source libraries such as the Modelica Standard Library. And the Modelica Standard Library is an extremely important library because it is the basis where we can find basic structure components, where we can then extend and create our own models in our own libraries. Modelica is designed to provide object-oriented, component-based modeling of complex cyber-physical systems. And on the name cyber-physical, you have two components. The physical related to the development of multi-domain behavior and components, where we can simulate different domains, mechanical, magnetical, electrical, etc. And cyber, because with the models that we create, we can also emulate the behavior of how software communication protocols and computing behaves using clocked variables and state machine constructs. And of course, system assembly is you have the opportunity to combine the components that you build and create systems and libraries. And of course, it's object-oriented and equation-based approach. Equation-based because the development of the components are all done through mathematical differential algebraic equations. And object-oriented, similar to Python, where you have inherent common attributes between models of a certain class, allowing for reusability. What OpenMPSL is now is it's a library that uses the Modelica language, and it is dedicated for power system analysis. It has power system components and phasor modeling simulation of power systems. One of the cool aspects of the library is that it has been verified against industry-grade power system tools, so it replicates the same response as those tools, in our case, PSSE. And the models can actually be used in multiple tools, so you're not limited to one software only. We can use our models in Dyanmic, OpenModelica, Model Impact, go for system modeler, etc. Okay. So now that I've described the introduction, let's go to the first block that I've developed, which is modeling of generic renewable sources. So WEC released a series of components that are meant to emulate PV, wind, and battery energy sources. And they're meant to be generic and modular, where you can play around and you can connect different versions of components. These are the REGC module components, REC family of components, and REPC family of components. Each one has their own usage. So one is for generator converter model, the injection of currents into the system. The other is responsible for the electrical control, and the REPC family is responsible for the plant level control of these renewable sources. The implementation of these components in OpenMPSL used components from the Modelica standard library, and also specialized blocks from the OpenMPSL, which are meant to reproduce integrator behavior in PSSE. And this slide is meant to exemplify how the modeling process is actually done. So these models that WEC released, they are glass box models, so you can actually take a look at the block diagram. And once you have the block diagram, which is the structure, which is the plant, you can then go ahead and implement it in OpenMPSL. So this is an example of the implementation for the generator/converter model. In a similar way, I've done the same construction pattern with the electrical controller. And here I'm only going to show the PV controller. This was also constructed for the wind and the battery controller as well. And of course, we have the implementation of the plant controller. And the previous two, this model and the previous one, the electrical and plant controller, they have logical switch blocks, which depending on the configuration and the logic on the switches, you can actually have different control schemes in these renewable sources. And of course, the implementation of these components has been done via block by block conversion. So you take components, you connect them together, and then you generate new models. Okay.
So, Fernando, one question.
Sure.
So to put these blocks, right, you need to have mathematical equations for the whole system dynamics for what you're implementing, right?
Sure. Yeah, it's on the models.
So that's from existing literature, or you have to do any? Did you have to do any additional extension?
So these models, they are based on WEC reports. So WEC released generic models that are ubiquitously used in the industry. And these are models that represent
WEC?
Western Electric Coordinating Council.
WEC.
Yeah, WCC. Yeah. And they released these components. They started releasing in 2015, their first version, and they're currently on their third iteration of these components. And when they released the models to the industry, they also released the reports with the block diagram of the models. You can then take them and recreate them in your own library. Okay. So the implementation process of the models, as such, is.
Is it correct that it's only block connections?
No. The majority of it is block connections, but there's also equations behind on the model.
Yeah, because you need to map it to the terminals. When I'm doing it now, that I have to actually do it myself, you have to match the PF component. You have to read the for initialization the power flow data and so on.
So the dynamics of the model is built through a component-based connection, but the initialization process under the hood is done on the equation section.
Okay. I haven't, I'm just playing with your blog, so I haven't used it that much, just trying to get it to work.
What do you answer the question?
Yeah, but they can ask later. or let's is one then. Let me check if it's one. Yeah. Yeah, no problem. What I want, okay, I can ask later when everybody else is, but this is not really correct. Even for the dynamics, there is still some equations behind.
Sure, but the equations are all represented by block diagrams. So you have integrators, have PI controllers. These blocks are represented there. They're all done through the connection. I don't have to manually write the equation with PI on the equation section.
No, not that. But go back. There, LVPL.
Oh, but these are components that I've implemented.
Okay. That's
They're user-defined components.
So
I implemented them.
yeah, but then
They're still in block form, right? You can still connect them.
yeah, but it has equations inside, or not more
But
blocks.
all of the components have equations inside.
Okay. So it's not really correct.
Sure.
Sorry,
No problem.
you know me.
Okay. So the implementation of the models is deemed the easy part. The challenging part is always going to be the initialization process. But for power systems, the initialization always starts through a power flow solution. And what a power flow solution is it's a snapshot of the electrical grid at a specific moment in time. And then you take the states of that snapshot, active, reactive power, and apparent power from the generation units, and voltage, magnitude, and bus and angle on the buses. And then you use those values in order to generate the initialization of the box in order for you to start steady state flat when you run the simulation. The last step of developing the model now is to validate the models itself. So I've implemented them, I've done the initialization. Now the idea is to compare the same model in two different softwares, specifically in PSSC, and see if the simulation results are the same. So I created the same model in both PSSC and Dynmic, applied a three-phase fault to see the dynamic response, and then check to see if they're equal. And from the simulation results, we can clearly see that they're one on top of the other. OpenPSL and PSSC are exactly the same. And the mismatch error is extremely small, with a root mean square error of 10 to the minus 5. And this was for a PV model using constant local reactive power control. So this was one of the many validation simulations that I had to run. Now comes the interesting part, which is the improvements of these generic models based on power hardware and loop experiments. And why should these generic models be improved? Well, WEC is always, WCC is always constantly updating and improving their own models since the first version of them. And one of the things is that WEC never released model validation procedures or results. So this means that the industry has to accept what WEC implemented, and the majority of the time they use without thinking what is under the hood on the models. So far, the methodology for building models, as presented in the previous slides, has been search the literature, implement models based on cell literature, and validate the implemented models against industry-grade power system software. And in terms of Lego analogy, it's looking at the manual and then implementing the toy, right? But now that we have real inverters with the power harness loop setup, what we can do is we can actually compare the real inverter against the developed generic model. We can then identify possible flaws and limitations of these models. And because we're using Modetica, we can exploit the Modetica language to customize the models as needed because they're open source. And we can then validate these new models against experimental data. And again, the analogy is the same. So that's the basic structure of the basic components. But now we have the real thing. Now we have the penguin, and which is the inverter. And then by comparing the toy against the real thing, we can actually update the manual itself. And then we can create a model that is more realistic and closer to the real thing. This is the analogy that I show. Now, what is the power hardware in the loop? Power hardware in the loop integrates physical power equipment with real-time digital simulation for power systems research and testing. And it's hardware linked to simulation, enabling energy exchange for virtual power system representation. So on the bottom of the slide, we have the representation. It's the diagram of the Alset Lab Volta power hardware loop setup. And you can see that we have three main blocks. We have the power inverter, the transformer, and the grid simulation. And in reality, the real equipment is in the power inverter and the transformer, as you can see in the pictures above. So we actually have a real inverter, which is the one that we're testing and validating against the models. And the grid simulation comes from the ORT grid emulator, which it emulates the rest of the grid where the inverter is actually connected. And the data that I acquired in order to modify the models is coming from the Schweitzer 735 meter. The data for model validation extracted from that meter over there. And with this information, we can actually then start tuning and creating these modifications to the model. The example that I'm showing here, this first add-on that I've added to the model, this was not based on the power hardware loop experiment, but it's a low-hanging fruit when you take a look at the model and their limitations. The original PV model is only intended for less than 30-second simulation, simply because the model only has one power profile in it. So it assumes that irradiance is constant for a range of 30 seconds, and then the simulation is only valid for those 30 seconds. But because we can actually create new components and connections with Model, and you can tune it, you can create the way that you want, this limitation does not exist. You can create an external component that actually provides multiple sequential irradiance to power profiles, and then you can connect it to the model without disturbing the original implementation, and you can have more information and more data. And the equation that I use for this is the irradiance power equation based on the Homer software. And the power now that is provided is related to PV rated power, PV derating factor, PV normalized irradiance, and PV temperature dependence. So I developed a simple simulation in order to test the model. And what I did was I found data for irradiance and temperature for Troy, New York. The data was acquired from the National Solar Radiation Database, and it was for June 1st, 2022. I took those values and I plugged it into the irradiance to power block. And I've also added to this simulation a three-phase fault that was applied at 440,000 seconds, so around 11:06 a.m. in the morning, and it lasted for 0.3 seconds. And the duration of the data they acquired for temperature and radiance is 24 hours. And while the original WEC PV model can only emulate one power profile, the add-on adds capability of simulating hours of power profiles based on temperature and irradiance value. So now the model is capable of describing more irradiance powers, and you can actually simulate more time. So for this one, no power hardware loop experiments were required. However, on this experiment, this one actually used data that comes from the hardware and the loop simulation. So this is the second add-on that I've added to the model. It's the voltage ride-through capability add-on. Voltage ride-through refers to the capability of an electrical device or system to maintain operation during temporary voltage disturbances or fluctuations in the electrical grid, typically caused by faults and disturbances. And real inverters, they have this voltage ride-through capability, but the WEC models, they are not capable, and this is described in the reports as well. The add-on was developed to mimic the VRT, voltage ride-through capability, of the inverter that we have in the hardware and the loop. And this is shown on the pictures down below. So down below, I developed a logic that adds the VRT, that mimics the VRT from the real inverter. I used integrators, switch blocks, and reset logic to reset the integrators. And the logic behind it is that the real inverter, if there is two time constants that you use. So one time constant is the ride-through duration, and the other one is the momentary cessation. So if voltage goes below or above a particular limit, and the time that it was below or above this limit is less than the time for the voltage ride-through, then nothing happens. The model and the inverter continue in voltage ride-through capability. But if it is below or above the max, and the time it stays below or max is above the voltage ride-through duration, then there is momentary cessation of the power injection. And after a specific amount of time, the inverter starts to inject current again and returns to pre-cessation state. And this simulation actually shows the limitations of the models. So if you take a look at the figures down below, what I've done was I've applied different voltage values at the terminal of the real inverter of the experiment. And these were changing. And at two moments, at the asterisk, at the double asterisk, the voltage actually dropped below the minimum threshold. But the first asterisk, it was less than the time for the voltage ride through. So the model and the inverter are supposed to continue injecting because it didn't surpass the time. But once it reaches the two asterisks, which is a time that it was above the 20-second mark, then what happened was that the inverter, the real inverter, and the model are supposed to drop momentary cessation and then return its injection. And that was only possible with the customized PV. With the PVs that have the RECB electrical controller and RECA, they're not even capable of replicating. One replicate does a weird behavior where values below the threshold, it immediately cessates. And for the RECB model, it doesn't even recognize the momentary cessation. It continues injecting power the same way. And this is reflected through just running a normalized root mean square error comparison. We can see that the custom model has a much smaller value compared to the other ones, simply because it can actually emulate better the response of the real inverter. So the power harder loop experiment showed to be an important ally in the development of more realistic renewable energy source models. Additionally, the open source nature of Modetic allows the user to build, test, and quickly devise, this is the important thing, proof of concept systems for model validation. But quickly devise systems in order to take these data that were acquired from the experiment and generate these experiments and validate these models. Okay, so now that we went through the implementation of one of the key models for my thesis, now I'm going to describe and talk a little bit about this third Lego block, which is as a Lego build, which is related to the resiliency and optimization of islanded microgrids using the secondary level MPC. Okay, so a little bit of a background of what a microgrid is. Microgrids are small-scale power systems capable of operating independently or connected to the main grid. And their purpose is to enhance reliability, resiliency, and efficiency of electrical systems, especially during outages or emergencies. This is because they can operate independently from the grid. Currently, we have 692 microgrids in the United States, which represents 0.3% of the US electricity. It's still very marginal, but microgrids are still a new concept. So there is a lot of research innovations that still can be explored, and this is where we have the opportunity. And when I said that it is resilient to outages and emergencies, this is what I wanted to show. The microgrid can actually operate while the utility grid is not even connected to it. So it operates in a islanded scenario. And when we're talking about microgrid resiliency, what are we actually looking at? So the image on top actually represents the stages of a microgrid when it islands, and then it has to reconnect eventually to the main grid. And what it has to do is it has to go through this period of islanded microgrid, and it has to be within quality constraints, and it has to be stable. So the idea of what we're looking is when the microgrid is islanded, the microgrid must be prepared for being separated from the main grid and operating alone. In the first stage, right after the islanding, the control static strategy is mainly concerned with keeping the microgrid online and resisting the initial transients from the disconnection. For the second stage, the microgrid must keep energy within the limited range in order to sustain energy quality and reliability. And on the third stage, when it's prepared to reconnect to the main grid, microgrid is prompted for resynchronization. And when the utility grid says, okay, you can reconnect, the microgrid is reconnected, close command is sent to the circuit breaker, ending the islanded operation. Okay. So I've used model predictive control as the control layer to control my microgrid throughout all of these steps. Now, what is it and why use MPC? MPC is an advanced control strategy that generates prediction of the plant model based on prediction model, so a linearized version of the studied system. The major advantages of MPC are that it's a multivariable controller that controls the outputs simultaneously. The optimization formulation already includes input-output constraints. And the key concept is the optimizer of the MPC minimizes a cost function for a user-defined length of a prediction through a prediction model, and the control length through the user-defined control horizon that you select. And despite the optimization being conducted for a control horizon, only the first control signal is selected through receiving horizon. And that is done repeatedly, iteratively. So every MPC optimization step, you're doing this and you're updating the control moves that are being sent to the plant. So linear MPC, it requires linearization of the microgrid model's differential equations, and it yields the ABC matrices from state space representation for the prediction of the variables. The linearized model is also used to estimate the observed states through Kalman filter. And the opportunity again here, using MPC and secondary control, is because it's a novel approach in microgrid secondary control applications. There's not a lot of papers describing MPC applications for secondary control. And the image just depicts a representation of what the MPC structure is. So I give the references for the MPC optimizer, and through the model that is used for the prediction model, which predicts the states of the system throughout a period, we can then optimize it through the optimizer, and it does that iteratively, updating control moves that are sent to the plant, and then based on the measured outputs, they're sent back to the MPC for, again, control moves and also to estimate states and estimate derivatives of the states.
Where's your common filter in
The common filter is inside the MPC.
the optimizer?
Yeah.
Yeah.
So how I've devised this control is through the layers of control inside of a microgrid. So microgrids, they operate in a hierarchical control configuration, and they typically have three layers: the primary level, secondary level, and tertiary level. These different levels correspond to different control tasks executed in different timescales. And for instance, the primary control is the fastest acting control layer of all of those three. And it's fast because it uses proportional controller, so it uses droop. But the problem with droop that we all know is that it has steady state error. And the task of the secondary level of control is to adjust those steady state errors by adjusting the references to the generation units. And this is done through the energy management system, through the secondary control. So the MPC control moves are actually the updates that are being sent through the energy management system, which then updates the power references in the generation units. So while devising the MPC,
But that doesn't exist, right? This is the idea. Then is that the EMS would have MPC.
yes, yeah, exactly.
That's correct, right?
Yeah. So typically, the secondary level control, it acts slower than the primary control, and it usually does this. It updates the power references in the time scale of minutes, 5 to 15 minutes, depending on the system. But the MPC approach, it does it faster because it did it in like 0.5 seconds. So it's continuously updating and improving and optimizing the microgrid through the whole entirety of the simulation. Okay. And while I was implementing the MPC framework, I've devised a proof of concept microgrid in order to test the components that I've used in conjunction with the MPC formulation. And the proof of concept microgrid, it was constructed to have a mix of traditional turbine generation units and the renewable models that I've developed. And in the diagram of the system itself, the proof of concept model, the microgrid is the one displayed on the red area, and the blue is the utility grid. And I'm interested in controlling only the microgrid through MPC, because when the microgrid is islanded from the utility grid, you don't have a connection to the utility grid. But the idea of the secondary control is to operate and control when the microgrid is islanded. The microgrid usually has one point of common coupling, which is the only connection point between the microgrid and the utility. And synchronous generators and the battery energy storage units on the model, they're the only dispatchable sources. Dispatchable because you can actually control how much power they're injecting into the system. And both of them have two inputs. The synchronous generator has mechanical power reference and excitation system voltage reference, while the battery energy storage has battery output power references and battery reactive power references. These are the inputs that are being controlled through secondary control. PV model is non-dispatchable, so we are assuming that the PV will always operate under maximum power injection. And for that reason, we only have one input that we can control, which is the reactive power reference. And the goal is to have an MPC controller that forces the microgrid towards a reference target. And this reference is ideally a condition that is ideal in terms of resynchronization, because the end goal is always to reconnect the system eventually to the grid. Now, the other system that I've devised, and this one is for the project itself, is one of the university campuses. This is one of the components that I've developed. And this particular university campus, which represents a real campus university, the model was built to emulate the electrical grid of a real university campus microgrid. And in particular, this microgrid only presents combustion and steam turbines. So they have in total 4 big synchronous generators. Again, the point of common coupling in the system is the only point of connection between the microgrid and the utility. And because we have 4 generation units, the system has a total of 8 inputs, 8 manipulated variables. They're updated via MPC. But despite having all these 4 units, the microgrid system rarely operates with all 4 generation units. Therefore, in reality, the number of inputs is reduced. And in the case of the example that I'm going to show, it only had 2 synchronous generators operating at the time, CT1 and ST2, so combustion turbine 1 and steam turbine 2. And again, the control is achieved through the same secondary layer controller with the energy management system. So now that we define the systems, this slide is actually to show the Modelica model that I've developed through these systems. And again, the same structure. In the red, we have the outlying microgrid components. In the blue, we have the utility grid. And in the green, we have the generation units. And because they are the dynamic models that actually control the microgrid system itself, they are the units that are used for the linearization task, as well as having the inputs and outputs. The output measurement and measurable states, as well as system variables, used for MPC tracking purposes. Dynmic, which is the tool that we use to run these Modelica models, it has a linearization function that, through the definition of proper inputs to outputs, it can actually give you the ABC matrices from state-space representation for the linear state-space representation of the microgrid. And in order to operate this with the MPC framework, we have to select proper measurements for the state estimation. And we have different states that are being used to estimate the states that are not being observed. And we have G2 states, PV, battery, and the point of common coupling where we have voltage, magnitude, and age. The same concept was done for the university campus, but now we only have synchronous generators. So we have states that are being observed through CT1 and ST2, and some states at the point of common coupling, which is the voltage magnitude. Again, these are the measurable states. These are used to also estimate the states that are not measured in the system. Now, one of the peculiarities of developing the MPC prediction model when using the renewable energy sources is that the prediction model is a mathematical representation of the system dynamics used to forecast the future behavior of the frequency control process. Now, estimating all dynamic states from the PV and the battery models that I've developed, the original WEC ones, using common measurements is not feasible. That is, while using the WEC models. Why? Because estimating the states of the PI controllers for both the renewable sources is not achievable. So you cannot estimate the states based on considering the typical output measures that we have in real world microgrids. So in order to implement a prediction model, what I had to do was I developed a reduced order model that was implemented for the renewables, where the internal states can be estimated, taking into consideration the typical output measurements of real microgrid systems. And subsequently, the reduced order model is utilized to formulate the MPC prediction model, which is then applied to the optimization stage. So what I've actually done is I developed 2 models. System 1 is the one that has the reduced order PV and battery energy storage components. And this model is being used with the reduced order models. And this model is used solely for the linearization purpose. So I used the simplified model to generate the linearized version that I use for the MPC optimization. And then I use this MPC framework on the full order model, which has the plant models that is controlled and is being measured. This one uses the original WEC models. Okay. So now that we've defined the system, now that we've developed the model, the next step would be to define the MPC constraints and cost function and the optimization protocol. And this slide is actually showing the MPC constraints and all these steps for the proof of concept microgrid. It's exactly the same structure for the university campus. The only difference is that the variables and the variables related to renewable energies are not accounted in the university campus. So the MPC constraints for a microgrid. They are tied to the microgrid operation performance requirements and also to the equipment limitations. And in summary, what we want to achieve is we always want our voltages inside the microgrid to be within a 5% margin of the nominal voltage level. And the frequency has to be within a tight band of plus minus 0.5 hertz from the nominal frequency. So as we can see from the constraints, I devised 10 different constraints for the proof of concept system. Constraints 1 and 2 are related to the max and min power that you can inject from the microgrid, and also the turbine rate of change and the rate of change of these synchronous of the turbine, the gas turbine. Similarly, on equations 3 and 4, we have the limits for the excitation system voltage and the rate of change of these variables. And then I assume that the power electronics components, they can actually change references extremely quickly. So I assume that there is no rate of change limitation to these sources. So there's only the hard constraints related to the limits of injection from G2, PV, and the battery. And of course, then we have the apparent power limits for all of the units, and we have the quality constraints, which is the frequency has to be bounded within a range, plus minus 5.5 hertz, and then the boundedness of the voltage magnitude as well. But once we have the constraints, the next step would be to define the cost function. And the cost function that I selected is a quadratic cost function, quadratic problem, where all the terms are quadratic. And the cost function actually has 4 terms, but the 2 that are the major defining terms for the optimization task is actually the first term and the third, which is related to the output reference tracking cost and the successive input move suppression cost. And they have weights that are attached to the variables that I'm controlling through the cost function. And it's a dual and a trade-off between a fast and a robust system. And ideally, what I've done in my systems is I've always chosen a robust application. So I tune the weights so that I'm penalizing big increments in input and output. So this way I can guarantee that I have a robust control configuration.
Okay. How you're solving this MPC? It's a quadratic programming problem.
Yeah.
So it can be solved very efficiently, right?
Yes.
Are you using Gurobi or something or?
I'm using the default solver that they use in the MPC package in MATLAB.
In MATLAB.
Yes.
Okay. And is the model getting updated? I think you mentioned something like that. The model is also iteratively updated.
So yeah, so I think I can explain on this. So this is a visual representation of this framework that I developed through Dyanmic MATLAB, and the idea is that it's running in parallel, the 2 softwares. So when you press play on both of them, what initially happens is that the MATLAB, it generates null input values and simulation in null input initial conditions. These are saved in a file. So what it's sending, what it's giving to the Dynamo script is that I'm defining a number of samples for the simulation. I'm defining the sample period, and it's also tied to MPC optimization rate, so the sample period. These values are sent to Dynamo, and through a Dynamo script, I then linearize the model once, and then I run one of the simulations using the full order model. And then the results are saved into a TXT file, and it contains the state values, the ABC matrix, and the final value of the states. These values are then sent to MATLAB, which is then the MPC it takes these values and then it estimates the states, the derivatives of the states, utilizing the counting filter, and then it generates the first control signal to be updated in the dynamic model. And these values are then sent again to Dynamo, and Dynamo reads these values that are updated through the first file that I generated through MATLAB, and then it runs the simulation for the second period utilizing the ABC matrices that were conducted in the first step, and then it does this back and forth until it solves for the entire simulation period. So in order to test the MPC framework, I've developed a couple sequence of simulations, but again, because of the duration of this thesis defense, I'm going to describe only 2 of the simulations that are present in the thesis document. So the first one is probably the most interesting result, which is the MPC framework actually controlling the microgrid throughout all of the stages of the islanding scenario. So it goes through ABC steps on the microgrid islanded scenario. And the objective is to compare the MPC controller actions post-circuit breaker trip across 4 different DR scenarios. These 4 are simply different energy sources that are being controlled. The first one only has G2. The second one has G2 plus PV. The third one is G2 plus the battery. And then the fourth one has all of the units being controlled in the microgrid. And the simulation that I ran is that the microgrid is abruptly islanded at t equals 0.55 seconds. And the control configuration scheme for MPC, the control scheme maintains VBus5, which is the voltage of the quantum common coupling, and is a specific reference that I selected, 1 pu, and a value of angle that is also I selected, 30 degrees, and the frequency has to be 60 hertz. And it does so from 0.55 seconds up to 30 seconds. And while it is doing this, the loads and the irradiance of the model are changing stochastically. So this shows that the MPC can actually adapt its manipulated variables when there's dynamics happening in the system. And then at t equals 30 seconds, the utility grid signals to the microgrid that it's ready to reconnect. And then for the 4 different scenarios, I test how fast they go and reconnect the system and what are the trade-offs. And for the simulation step, I selected a control horizon of 2, the prediction horizon of 20. And these are the MATLAB default values. These worked really well. I'm going to show on the next one that I have to select a different value for those. And for the solar irradiance, I selected a low variability scenario with a baseline of 700 kilowatt per meter squared of irradiance and a 0.002 standard deviation that adds noise to the power injection of the PV. And the important thing is that the common filter state estimation is being applied at 0.05 seconds, so it's a faster rate than the actual update of the MPC. So states are being estimated much quickly than the MPC optimization task. And the table on the bottom shows the pre-islanding steady state scenario of the system, so before islanding, and the manipulated variable constraints for all of the generation units. And in terms of just visual representation, initially the microgrid is consuming power from the utility grid. But then with the open of the circuit breaker at 0.55 seconds, what happens is it tripped the circuit breaker and then the microgrid is islanded from the main grid. And after it goes through the resynchronization process, then it reconnects and recloses the circuit breaker. And these are the results for the simulation. So the first 2 plots that I'm displaying here are actually to check the feasibility of the solution. So what I've devised here is I've tracked the variables and I placed them without this frame of the performance constraints, where voltage has the 5% margin and the frequency has to be plus minus 0.5 hertz from the nominal. And what we can see is that for all 4 scenarios, all of the states that I'm measuring are actually within the feasible regional operation. So this means that the MPC is controlling and the variables are being controlled and they never went outside of the quality values of the constraints. This slide shows the results of the manipulated variables. So depending on the control configuration, we'll have 1, 2, or all of the sources being controlled. So that's why, for instance, on plots C, D, and E, where we have QPV ref, so reactive power control reference on the PV, power reference on the battery energy storage system, and reactive power reference on the battery energy storage system. That's where we see that in some scenarios we don't have the control of these sources, but all the sources are being controlled, and the outputs are actually display that the MPC optimization worked really well. So in all of the 4 cases, all of them managed to reach the steady state, the 60 hertz target. And of course, because the scenario where we have the battery energy storage system, we can actually control injection of power. That scenario is actually reaches 60 hertz much quicker than the one that only has G2 or G2 plus PV. And that is shown on the first plot, microgrid frequency. But again, the controller is also changing the magnitude of this. And it started at 1 PU, and then at 30 seconds through the start of the resynchronization process, it changes the references until the moment of resynchronization. And the simulation started throughout that first period through 0.55 and 30 seconds, trying to go to a target of 30 degrees for the bus angle. And then eventually it goes and matches the point of common coupling angle on the other side of the microgrid. And that is also shown on C, so it did its job. And of course, we can see the usage of the battery in all of these scenarios. So the plot E is showing that depending on the configuration scenario, when we're using the battery, the state of charge of the battery is decreasing. But when it's not being used in scenarios 1 and 2, the battery continues to charge. And of course, the key result of all of this is that we want to mitigate the transient torques that can be applied in the torque of the synchronous generators when we have resynchronization. And in all of the scenarios, when we have the resynchronization, where marked by those areas, the torque, the active power transit is very small, meaning that the torque applied to the rotor at the moment of the resynchronization is also small. So all these steps passed. The difference is that with more dispatchable sources, you can do this in a much faster pace. And of course, for simulation 2, we have the university campus islanding scenario. And this result, I wanted to show the impact of communication systems delay for a realistic system, a more realistic system. So the objective is to test the MPC-based secondary level control, considering different levels of communication delay values. So I've had 4 different scenarios again, with increments in the communication system delay. And the first communication system delay of 0.05 is actually a window where we have a delay that represents the calculation of the Kalman filter and also the optimization step. So the optimization step and the Kalman filter, on average, the time it takes to generate the optimization step and the Kalman filter are less than 0.05, which is the tick rate for the estimation state. That's the first one. And what I did is I added 0.1 seconds to communication delay until I reached 0.35.
Sure. So, when are you, at what frequency are you computing the MPC or recomputing the MPC?
So the MPC is being done at the same rate as the previous one, so at 0.5 seconds. So it's optimizing every 0.5 seconds.
0.5 seconds. And the communication delays are again?
So they are less than
less than
yes.
that.
But I'll show an important result. That is, the IEEE has a standard, the 2030.7 standard, and this is a standard that is exclusively dedicated to discuss requirements of control microgrids. And they have this table where they have the maximum latency requirements in the communication protocols and microgrids. And for controls, they actually limit, or the maximum limit latency required is actually 100 milliseconds, so 0.1 second. So what I'm doing is I'm stressing my system much more. I'm testing the MPC for its system delays that are above the maximum threshold, and it still was able to control the system. So the simulation, what I've done is I've also tested and I landed the microgrid at 0.55 seconds. And the control scheme maintains the voltage at the point of coupling, the BUT02, at 1.018 PU. For this particular example, there is no target value for the angle of the bus, and I'll explain why. So it's free to roam, but the frequency has to be in 60 hertz. And the control setup for this one, I chose a more robust setup. So control horizon is actually 10, so this will make the update of the manipulated variable slower. But the prediction horizon is still the same 20 value, 20. And the loads also include noise and then mimic the load demand profile through a sinusoidal source. Again, the same concept, but this time power is actually being injected to the utility before landing, and then it trips, so the micro has to operate landed. That is the simulation that we're in. And again, I start with the feasibility region of operation. So this plot again shows that for all 4 different types of delays, the states that I'm measuring, they are within the boundaries that I've devised, that are the power quality, the the frame performance constraints. So voltage within 0.05 pu, and the frequency is in between the type band of plus minus 0.5 hertz. We can see that there's a starting point for the states, and then they all go back to an endpoint, which is the target value that I selected. Now, why did I not control the angles in this particular example? Is because by having two synchronous generators, which is the case of this utility grid, if you actually impose a target to the angle, both these generation units, they are transitioning. They are either accelerating or decelerating in a combination. And by doing so, it takes much longer for you to actually reach the angle, the target angle. So if I had selected a target reference for the angle of 0 degrees, it will take roughly 65 seconds to reach that target. While in the previous case, where I only had one synchronous generator, which was the reference synchronous generator, that one goes much faster. So what I've done for this simulation is that I've eliminated the target for the angle, and this way the NPC can actually control the microgrid much faster. And the plots they display the results for the different delays, and even for delays that are much above 250% more than the maximum latency required by the IEEE 2030, even though we can still see that the results point to the fact that the optimization can actually control the microgrid towards its references. And here we're actually looking at the observed output variables. So A and B are actually the frequencies on those two, the frequency of the rotation of the generators on the combustion turbine and the steam turbine. And C and D are actually showing the voltage magnitude and angle of the point of common cut. And again, you can see through the plot D that there is no value target for the angle. So it's free to roam wherever it goes, as long as the NPC actually optimizes the other two parameters, which are voltage, magnitude, and frequency. And this way, it reaches a steady state again much quicker than those 75 seconds. Okay, so now that I've went through the results, I'm just going to briefly mention other results that were not presented here, but were added to the thesis itself. So the contents that were not discussed in the presentation were some of the Modetica models and some of the simulation results. And these are related to the library that I've implemented for multi-domain simulation of motors, and the validation results that were conducted with this library. All of these three-phase multi-domain validation examples, up to a multi-domain system example comprising electrical and fluidic domains. On the university campus framework, I haven't described an in-depth explanation of how the university campuses were developed, and I didn't also discuss the record structure. And on the simulation results, there are multiple simulations that were conducted in order to validate, in particular, for instance, the consequences of microgrid landing and improper resynchronization. And on the MPC framework, in-depth description of the generation unit models that are used, and an explanation and an in-depth explanation of the state-of-the-art methods for microgrid frequency regulation and synchronization, which I found and compared against MPC. Those are not also presented here, and the results were also not shown. So in conclusions and future work, so for the conclusions, I was able to fill a gap in the Open Cell library by adding renewable energy sources that are vital due to the rising renewable penetration in our current system. I've gained experience gained by developing these models led to proposing improvements to the original WEC-based renewable energy sources. I've released a dedicated GitHub repository with the data-enhanced renewable models to promote the collaboration and knowledge sharing among the modeling community and power system engineers, facilitating the adoption and advancements in the laboratory setups. I've also had the creation of a new Modetica library that is focused on modeling induction motor configurations and variable speed drives. The library is designed to easily connect with various Modetica components from different libraries, facilitating the integration of components from diverse domains into one comprehensive system model. I've also developed microgrid models that are suitable for proposing innovative optimization algorithms. And then given the appeal towards increasing system resiliency through microgrids, these microgrid models can actually serve as a basis for testing different control schemes such as MPC. The systems are open source, because of the modeling language that we select, the model. I also developed microgrid models to support the development of innovative algorithms. Simulation results involving secondary level control using MPC display the efficacy of the advanced controller in maintaining islanded microgrid system operation. Not only that, the same controller is capable of resynchronization. So the control architecture is capable of reaching different goals based on modifications to the MPC reference signal, thus eliminating the need of multiple different controllers in a microgrid, which is applied nowadays in microgrids. And as future work, I would like to highlight that there's still to continue the movement towards these open source models and power system analysis, leveraging the effectiveness of the Modelica as a valuable engineering modeling environment. Enhance the existing framework to ensure a more robust and efficient implementation of the MPC for Modelica models. So consider, for instance, incorporating readily available and free to use Python libraries to facilitate this process. The exchange file framework, the way that I've implemented the MPC framework, although effective, it can be slow. So that's one of the limitations. Other feature would be to investigate the potential of distributed model predictive control as a feasible extension and improvement over the centralized MPC framework discussed in this document. And lastly, explore the application of MPC in the setup where we have multi-domain systems, the coupling between the thermal and the electrical side, with the optimization of various domains with distinct time frames. And with that, these are my published papers. And this is a list of the papers that are currently under review. And with that, I would like to thank your presence here. Thank you.
Thank you very much, Fernando.